Good morning. In the last session I have started covering the surface and internal quality in continuously cast product. I have mentioned what are the imperfections in cast product, what are the possible imperfections, what are the types of imperfection in cast product. I have mentioned about this blowhole, pinhole, then crack, depression, oscillation marks and segregation, how are they influenced by casting process or the specific steel grade, what are the casting type of alignment. These are the possible factors. I have started the different issues one by one. I had mentioned about how these blowholes and pinholes are generated. I mentioned that the whole idea is to control the content of soluble oxygen, nitrogen and hydrogen. If we can control this, then the partial pressures of hydrogen, nitrogen and CO will be less during solidification, and there will be less amount of gas bubbles formation, because the total pressure, which is a summation of partial pressure of hydrogen, nitrogen and carbon monoxide, will be less than the atmospheric pressure or the ferrostatic pressure. So, there will be no gas bubbles which can generate, which will form in the cast product. So, this is the basic principle for avoiding blowholes and pinholes in the cast product. Then I have mentioned that when the solidification is starting in the mold, there we call it primary cooling in mold. So, how it happens? Liquid steel that gets drawn into gap between mold and solid shell. So, this part of slag freezes in contact with cold surface of copper mold. So, this I am trying to show with an image like what is happening in mold. This is the mold surface, copper is a water cooled mold surface, and we have the sub-entry nozzle here. So, the liquid steel is getting discharged from the port of the sub-entry nozzle and getting inside the mold. Now, if you look at the inside the mold, what is there? This is the liquid steel, this is the liquid pool of this whatever powder you are adding at the top of the liquid steel in the mold. That powder is going to get melted in contact with the hot liquid steel. So, there are basically 3 layers. One is the loose powder at the top, then the sintered layer, and finally the liquid pool of slag, which is just at the top of the liquid steel. So, basically in the mold we have a loose powder, we have a sintered layer, we have a liquid pool on top of the liquid steel. So, what is happening is important. The horizontal heat transfer is taking place this direction, because it is a water cooled mold. This is the liquid steel which are having some lot of high temperature. So, heat from here will try to come out through the water cooled mold. So, this is a horizontal heat transfer. I have also told that some amount of heat will also like to come out from the liquid steel to outside in the vertical fashion through the powder. So, the amount of heat of course is less compared to this, because there is a big insulator. Loose powder is a big insulator, it does not allow too much of heat to come out. So, this surface also has to be maintained hot. So, otherwise there will be some heat loss. So, if the surface is maintained hot, then this heat transfer is relatively less. And here you have this is a horizontal heat transfer, some small amount of heat transfer vertically. So, some amount of radial heat transfer also will be there. So, what happens is that one rim is formed, is called the solid rim, which is forming from the liquid pool of slag. So, this molten slag, after it gets frozen, this is a rim, and then what is happening, please look at here, this is a liquid slag, then this is the rim, and then this dark area is basically the solid slag. So, from the liquid slag which is in contact with the mold, copper mold, some amount of solid slag has formed. This will be clear, more clear rather in this picture. Here this is the mold area, this is the flow in the mold. People have found out through some modeling what is the flow, what is the type of flow. The liquid steel is coming inside, this is the temperature distribution. It is very hot here, and then slowly the temperature is coming down inside the mold. So, this area, that means the meniscus area has been magnified and shown in this picture. So, you please look at here, the molten steel is this yellow, we have the shell, solid shell which is forming in contact with the molten steel, the part of it is getting solidified to this is the solid shell, and then we have the liquid slag in contact with the molten steel, then we have a solid slag and solid rim, and finally the mold. So, the gap between the mold and the molten steel, as I was telling you, the solid slag will first the liquid slag will be dragged in, and in contact with the mold this will get solidified. So, we have a layer of solid slag and then liquid slag and then the solid shell and of course, the molten steel. Now, this particular area if it is magnified, look at the sizes. What are the sizes? This 5 millimeter is this much. That means, from the liquid shell thickness here is hardly, when it is starting to solidify in the mold, at the top of the mold is hardly less than 1 millimeter. It is increasing as you are going down the mold. Maybe here it is 2 millimeter or 3 millimeter. As you are going down, the shell thickness will increase, but at the top of the mold it is hardly 1 or 2 millimeter. So, this area is again, if it is magnified, you see what are the different phases which are present. What is the solid slag film? This is the liquid slag film, and this is the shell, solid shell which is getting solidified. So, this liquid slag will generate, because of the movement of the oscillation, the vertical movement, top and bottom, this movement of the mold, this will generate oscillation marks at this shell. So, these are the oscillation marks which will be forming. At the meniscus, I have shown what is there is a molten steel, on top of that liquid slag, on top of that solid slag. So, this is the area, meniscus area which has been magnified, and this particular area has been magnified here. So, as I was telling that the primary cooling on the mold, the liquid slag is getting drawn into the gap between mold and solid shell because of the mold oscillation. Then part of the slag freezes in contact with cold surface of copper mold, as I had shown you in those figures, and this relative thickness of the solid vis-a-vis liquid slag layer in the gap, this is very important. Part of it is solid, part of it is liquid. What is the relative thickness? That determines what is the heat transfer. How is it controlled? Controlled by two factors of the powder of the mold, or the mold powder or the mold slag. First is the basicity, what is the ratio of calcium oxide SiO2, and the solidification temperature of slag, they play important role. So, if you have high solidification temperature, then what happens? As the liquid slag is getting solidified, that means high solidification temperature means it will get solidified at relatively higher temperature. So, at a particular temperature lower than that, the higher the temperature, thicker will be the solid shell, solid layer of the mold slag. So, this is important. High solidification temperature increases solid layer, and high basicity of the slag, this facilitates crystallization. That means, from the slag which is slaggy in nature, from slag it will go to the crystalline phase if you have a high basicity. So, both of these will lead to lower heat flux, this is important. So, during primary cooling, how the heat flux in the gap between the shell and the mold, how it is dictated by two factors of mold slag. One is the basicity and is the solidification temperature. So, these two factors will determine what are the relative thicknesses of solid slag layer and liquid slag layer. Now, if you have a air gap formation in case of shrinkage, then air is an insulation causing insulation, that means an insulator. So, this will have lower, the heat transfer will be affected. So, this is again very important to understand how the cooling is taking place in the mold, what are the causes of heat transfer, the horizontal heat transfer which I was showing here, how this horizontal heat transfer is dictated by the two layer thickness, one is the solid layer and the liquid layer. The relative thicknesses of this solid and liquid layer will determine the horizontal heat transfer, and this will determine how the shell will grow. This is very important to understand. The same thing I have seen in this figure, this meniscus, you have basically molten steel on the top of that liquid steel, on top of that liquid slag, molten steel on top of that liquid slag, and then you have a solid slag. So, solids here in between the gap of the solid shell which is forming and the mold which is relatively cooler because of the water cooling inside. So, here you can see the solid slag, then you have a liquid slag and then the shell. The surface of the solid shell, as I have told, we have lot of oscillation marks. Now, what are the depth of these oscillation marks? That will determine whether the surface is good or bad. There will always be oscillation marks, since there is oscillation during continuous casting, mold oscillation, there will be oscillation marks. But the question is whether they are deep or not. I will come to it. What determines the depth of the oscillation marks? If you have deep oscillation marks, it is not desirable. So, it is very important to understand what are the factors which create deep oscillation marks, which is a quality problem on the surface of the solid shell, and finally, the surface of the steel cast steel, whether slab or bloom or billet. So, oscillation mark will be there, it is part of continuous casting, but we do not want deep oscillation marks. That is what is important to keep in mind. Now, please look at here what is happening. This is showing how the oscillation marks are forming in the mold. What are the mechanism of formation of oscillation marks? This is the solid shell. On surface, I have told the oscillation marks are forming. Now, please look at what is happening here. The mold is oscillating, let us assume, which is the most common oscillation form in a sinusoidal fashion. So, this green dotted line indicates the movement of mold, in a sinusoidal fashion, okay, in the vertical direction. Yeah, the mold is going up and down, and the movement, the displacement is sinusoidal, that means going up, going down in a sinusoidal fashion. Now, if you differentiate this, you get the velocity of the mold. This is Vm, this is that black line. This is also sinusoidal, but at a phase angle from the displacement. Displacement was this green, and the black one is a velocity. Now, what is casting speed? Casting speed means the solid shell or the strand which is always coming down. The mold is going up and down, up and down. So, some part of the movement of the mold is up and then down, but the strand is always coming down, then only the continuous casting is taking place. So, the strand is coming down. So, what is happening is, try to understand what is happening. The mold is going up and down, there is a velocity profile of the mold. Since the displacement is sinusoidal, the velocity is also sinusoidal, but at an angle, phase angle with the displacement, but it is a sinusoidal velocity also of the mold. But You see Vc is the casting speed, that means the strand at which the liquid, the shell, everything is coming down, that means that the strand is coming down. So, this is fixed. Okay. So, this is this blue line. So, the blue line is always, if this is the 0, 0 line, so blue line is always down, but this mold velocity is sinusoidal. That means at certain portion of the cycle of its movement, it is going up and then it is going down. So, please try to understand that at certain portion of this sinusoidal cycle, this portion, what is happening? Here this blue line is the velocity of the strand, the casting velocity, casting speed, and this one is the velocity of the sinusoidal velocity of the mold. So, this portion, the velocity of the mold is less than the velocity of the casting velocity. This is the whole cycle, please try to see, this is the whole cycle. So, in the whole cycle, some portion of the cycle, the velocity of the mold is upwards, or it is higher than the, or larger than the upwards, relatively upwards compared to the casting speed. But at certain portion of the cycle, it is more, at the lower portion the velocity is more, downward velocity is more compared to the velocity of the casting velocity. So, this portion of the cycle causes oscillation marks. Please try to see. This is the area which is called Tn. Tn is negative strip time. That means the cycle time where the velocity of the mold is less than the velocity of the casting. This is called negative strip time. So, in the whole cycle, there is some portion of the cycle where the velocity of the mold is more than the velocity of the casting speed. So, that portion of the cycle is called, or the time is called, the positive strip time, and when the velocity of the mold is less than, or relatively less than the casting speed, is called the negative strip time. Less than means at the downward velocity I am talking about. So, that means this is the negative strip time. So, this mold oscillation and heat transfer, now look at what is happening to the heat transfer. Because of the oscillation mold, heat transfer, there is a base heat transfer, on top of that there is a cycle of heat transfer. The base heat transfer line is this, maybe it has been calculated, this is basically, this figure is based on some modeling. So, some calculation has been done. So, the base heat transfer line is say 3.37 megawatt per meter square, and then there is a oscillation in even heat transfer. This oscillation in heat transfer is basically because of the oscillation of the mold. There is oscillation of the mold displacement, there is oscillation in the mold velocity. So, there is a oscillation in the heat transfer as well. So, look at what is happening. Heat transfer here is maximum 3.45 at the peaks, and at the trough it is relatively less, 3.30. So, average is 3.37 along this line. So, there is also some cycle in the heat transfer, in what is happening in the mold. Now, look at here where this negative strip time is taking place. Negative strip time is taking place, as I have mentioned, when the velocity of the mold is relatively lower compared to the velocity of the casting, velocity of mold less than velocity of casting. So, negative strip time is this part of the cycle in time, in second. So, we find that oscillation marks are forming in these regions, but look at what is happening at some depressions in the inner side of this is the solid shell, this is the outer shell, this shell is forming here, this is the inner shell, that means the shell is increasing in this direction. Heat is being taken this direction, so it is increasing in this direction. So, it is inner depressions is where the relatively it is coinciding with the relatively lower portion of the cycle of heat transfer. This is the lower portion of the heat transfer. So, this is coinciding with the depressions. So, depressions are basically coinciding with the lower portion of the heat transfer. That means, when the heat transfer is slightly lower, the depressions are also forming. So, oscillation marks are forming during negative strip time. We have to remember high is the Tn value, that means higher is the negative strip time, that means in the whole cycle of say 1 second or whatever it is, a few microseconds, what is the portion of that in the whole cycle which is having a negative strip time. The more is the negative strip time, more will be the deep oscillation marks. So, as I was telling you, deep oscillation mark is a defect. So, this is related to high negative strip time. Now, try to understand what is negative strip time. It depends on what? If you have higher casting speed, then what is happening? This blue line is going down. So, in the whole cycle, the portion of negative strip time also will be less, because this is low. If the Vc is relatively high, that means casting speed, your negative Vm, which is sinusoidal. So, the portion of Vm when it is less than Vc will be relatively low. So, negative strip time will be low, less. So, slightly higher casting speed is beneficial. You have relatively shallow oscillation marks, because negative strip time is less, oscillation marks also will be relatively shallow. So, casting speed is one factor. What are the other factors? Other factor is the frequency. If you have very high frequency, then negative strip time also will be less. Mold is fluctuating in a frequency and amplitude. There is both a frequency and an amplitude. The frequency, that means the number of cycles per second, that is called frequency. If you have higher number of cycles per second, that means the frequency is high, then you have relatively less negative strip time. If the amplitude is small, relatively less, then you have less negative strip time. So, what are the factors which are helping in having low negative strip time? Higher frequency of oscillation, lower amplitude of oscillation, and higher casting speed. So, these three factors during sinusoidal oscillation of mold will give us or will indicate what is the negative strip time, and if the negative strip time is low because of high frequency, less amplitude and high casting speed, then we have shallow oscillation marks. So, which is not a defect. We have deep oscillation marks, we have a defect. Now, I have talked about the casting speed. Of course, there is a limit of casting speed. If the casting speed is high, then the shell thickness, I think I will just discussed in the last session. Today also I will discuss. If the casting speed is high, that means the heat transfer, how it is will change the shell thickness also. The shell thickness also will be less. So, there is a limit of increase in the casting speed, but what I am telling is within that limit, if you operate at the higher range of the casting speed, within that safe limit, you cannot go to very high casting speed, because then the shell will be thin, and because of the lot of stresses, lot of strains and stresses which are forming on the shell, there might be rupture of shell. So, that is not desirable. So, the casting speed, there has to be a limitation, and within that limitation, if you operate at a high casting speed, the negative strip time will be less. We should have high frequency of oscillation, negative strip time will be less. We have less amplitude of oscillation. So, the negative strip time also will be less. So, we have shallow oscillation mark, this depth of these oscillation marks will be shallow. So, we have relatively better quality of the casting.